small permanent magnet. You can see that it's a magnet because it lifts steel objects. We'll cover the magnet with a thin sheet of paper. This salt shaker is filled with tiny bits of iron called iron filings. Now you know what's going to happen. You've seen this before. Perhaps you've done it yourself. As the iron filings fall onto the paper, they form into a pattern over and around the magnet. But why do the iron filings form in a pattern? It's because each one of these iron filings is being acted on by a force. Each of these little bits of iron is affected by the force of the magnet, even though the magnet isn't actually touching any one of them. A region of space like this, where at every point a force can be felt, is called a field. The space around this magnet is called a magnetic field. If we bring a small compass into the magnetic field, we can see that it too is affected by that field. So although we can't actually see a magnetic field, we can see the effect the field has on objects that are brought into it. Fields are invisible, but they make their presence known in many different ways. For instance, if I stack these little ring magnets on a pencil, the magnetic field around one pushes against the magnetic field of the next, keeping them apart. I can squeeze them together, but the magnetic field will push them apart again. I can push one magnet up a hill with another magnet without the two magnets touching at all. The magnetic fields around the magnets keep them apart. Well, you can't see the field around a magnet, but you can certainly feel the effects of it. And you can see the effects of that field on iron and steel objects. Now let me show you a different kind of field. This is a steel rod. You've seen how the field around a magnet attracts steel. This is the glass rod, but glass is not affected by the field. It doesn't have any effect on wood. Or, for that matter, this old shoe. Now let me show you something else. This is a plastic rod. Now this rod doesn't affect this shoe either. But watch. Now there seems to be a field around this rod. This rod attracts the shoe without actually touching it. But the field around this rod is not a magnetic field. We've just seen that magnets don't attract shoes. Actually, by rubbing this rod, I've placed an electric charge on it. And around any object with an electric charge is an electric field. The electric field attracts the wood, and the glass, as well as the steel. You can't see the electric field around the charged rod, but you can certainly see the effect it has on different materials. This little box is made of very thin paper, and this is a metal sphere that has been given an electrical charge. Notice how it attracts the paper box when I bring the box near it. Now here's something else I want you to notice. No matter where I move the box around this charged sphere, the box is always attracted so that the string points to the center of the sphere. An electric field seems to extend out from the sphere in all directions. You know you can't actually see a field, but this drawing does suggest how a field extends out in all directions from the source of the field. What makes the paper box fall when I move it away from the sphere? Well, it looks obvious enough. The electric field pulling on the box gets weaker and weaker, and we say the box falls. But what makes it fall? Have you ever stopped to think that wherever you are on Earth, you are in the midst of a field where at every point a force is felt that is trying to pull things down? That kind of a field is called a gravitational field. I can tell that I'm in a gravitational field right now because if I raise an object up in the air and let it go, a force pulls it back down. That force is called gravity. There is a gravitational field around every object. For example, there's a gravitational field around this pencil. But the gravitational field around a small object is so weak that you don't notice it. However, the Earth is a huge object, and the gravitational field around it is strong enough to be noticed. Everything on Earth, including that city down there, is held down by the Earth's gravitational field. If I jump away from Earth, you know I certainly won't stay up here. The force of gravity will pull me back down to Earth again. Like the other fields we have studied, gravitational fields extend out in all directions from the source of the field. Remember that when we move the paper box in the electric field around this charged sphere, it was always pulled toward the center of the sphere. Well, the same thing happens in a gravitational field. Here is the Earth with its surrounding gravitational field, and here is New York City. If a boy in New York lifts a brick up and lets it go, it will fall to the ground. In other words, it will fall in this direction, toward the center of the Earth. To a boy in New York, that direction is down. Now, what if in Australia something is raised up in the air at the same time and let go? What happens then? Well, it falls toward the center of the Earth, too. The only way people on Earth have of telling which way is down is by feeling which way gravity is pulling. So to someone in Australia, the scene looks like this. To a New Yorker, down means this direction, but to an Australian, down means this direction. Wherever on the Earth we drop something, we say it falls down. But actually, it falls toward the center of the Earth. The gravitational field extends out from the Earth in all directions. The farther away from the Earth you are, the weaker the gravitational field is. But 239,000 miles away from the Earth's gravitational field is still strong enough to hold a moon in orbit. The unseen force of the Earth's gravitational field holds the moon in orbit. That force is just as real as the wire holding the metal ball in orbit around this athlete. In science, a field is a region of space in which, at every point, a force can be felt. There are magnetic fields around magnets, there are electric fields around objects that have an electric charge, and there are gravitational fields around all objects. Now, take a look at this. The needle in this compass is magnetic. Normally, it points towards the north. This is an electromagnet. There is a magnetic field around the electromagnet only when electricity is flowing through it. Now, I'm going to turn the electromagnet on and off in a particular way. Watch what happens to the magnetic needle. It takes energy to make the needle move back and forth, and that energy seems to be coming from the magnetic field of the electromagnet. Can you think of any other kinds of fields that are used to carry energy from one place to another?